Okay, folks, thank you very much. Today we have our presentation titled it The Weird, Wonderful, Wild World That We Call Home, Physics from Light to Unification. Today we're going to look at the strange case of the cat that's alive and dead at the same time, a photon's eye view of the world, black holes and naked singularities, the Big Bangs, plural, and the collapse of the state vector. But first, this is actually part of Texas curriculum. These are our learning objectives. These are the TEACs. First is that students will be able to describe the dual nature of light. We're going to get to that. It's really important. The next is that you'll be able to explain the impacts of the scientific contributions of a variety of historical and contemporary, that means current, scientists on scientific thought and society. Remember, what we do in science doesn't end in the lab. And the last is to describe the historical development of the concept of gravitational, electromagnetic, weak nuclear, and strong nuclear forces. We call these the four fundamental forces because they are, to our knowledge, the four forces that make the universe work. Let's begin. Now, in the beginning of science, we had the scientific method. Now, the scientific method is, and always has been, essentially a method of trial and error, guess and check. We first developed it when we started having written language and we were able to look at the world around us and try to figure out cause and effect. What happened? What would change it? What caused it? It was formalized in the 11th century by Ibn al-Haytham. He was a physician and a scientist, and he realized that experimentation and observation were critical to learning about the world around us. Because you can never be sure until you've checked and checked and checked. You can still be surprised. This was the beginning of the scientific method, and it happened in the Arab world because after the fall of Rome, we lost access to most of our knowledge. Most of the books, most of the scrolls we had were gone. They kept it in the Arab world. So while we fell a little bit behind, science as we know it started there. And then, in the Renaissance, we began rediscovering that lost knowledge, or knowledge that was lost to us. And one of the greatest geniuses humanity has ever known was born in England in the late 17th century, Sir Isaac Newton. You already know him from Newton's laws. This guy was smart. He realized that the world around us works on the rules of mathematics. Given the mass of an object, the coefficient of friction, the angle of a ramp, I can tell you with complete precision, in a vacuum, its acceleration, its velocity after a given number of seconds. I can draw you the component vectors with complete accuracy. The world works on math. And Newton wanted to actually describe the world. So him, along with a guy named Leibniz, created calculus to explain what he saw. Right? He created it. You thought studying for exams was rough. He also told us about the first of the four fundamental forces that we came to understand, and that's gravitation. It's going to be our next unit. What that says is that F1, force 1, is equal to force 2. There is a mutual attraction between any two objects in the universe, no matter what distance separates them. And we know also, by Newton's third law, that forces are paired. So it's equal between those two. The Earth pulls on a speck of dust with exactly as much force as that speck of dust pulls on the Earth. The second of the four forces that we came to understand is electromagnetism. Michael Faraday was born in London, and he was born to very humble beginnings. His parents were poor. He never had an advanced formal education, but he was curious. He was dedicated. And even when high society didn't want him, he kept up. He eventually made one of the most important inventions and discoveries for our modern world, which was the electromagnet. That's what we use for both generators and motors. We wouldn't have most of our modern machinery if he hadn't realized that electricity and magnetism are the same thing. Now we know that both electricity and magnetism are the same due to a few things. So let's start off with that.
Now, electromagnetism is a force that had itself been unified only a few decades earlier. In the mid-1800s, electricity and magnetism were sparking scientists' interest. These two forces seemed to share a curious relationship that inventors like Samuel Morse were taking advantage of in newfangled devices such as the telegraph. An electrical pulse sent through a telegraph wire to a magnet thousands of miles away produced the familiar dots and dashes of Morse code that allowed messages to be transmitted across the continent in a fraction of a second. Although the telegraph was a sensation, the fundamental science driving it remained something of a mystery. But to a Scottish scientist named James Clerk Maxwell, the relationship between electricity and magnetism was so obvious in nature that it demanded unification. If you've ever been on top of a mountain during a thunderstorm, you'll get the idea of how electricity and magnetism are closely related.
When a stream of electrically charged particles flows, like in a bolt of lightning, it creates a magnetic field, and you can see evidence of this
On a compass.
So, we had one of our assumptions about the world changed. First of all, people didn't think force could act at a distance. Show that it can. You can use a magnet to move another from a distance away. We also thought that electricity and magnetism were separate, which makes sense if you look at it at first blush. I've never been able to power my TV by waving a magnet near it, and I've never been able to attract things by turning on a light bulb. It turns out that that's a delusion of limited perspective. Faraday's work was perfected by a Scottish scientist, James Maxwell. Now the equations he came up with aren't just math. What they are is what makes iPhones, tablet PCs, modern computers, and of course sharks with laser beams on their heads all possible. Give me one moment, please. Mr. Shelley speaking. Yes, I've spoken, and I'll be sending something on over real soon. Thank you. Thank you. Have a good weekend. Bye-bye. Okay. Now, they work. We know they work. And because they work, we know that the math, what it says, is probably true. Remember, we're never sure. Science deals with refutation, with proving things false, and coming up with best fit models. So we might be wrong, but it seems pretty strong. And in that context, think of electricity and magnetism like light. If we split light through a prism, we get different colors. Just like with electricity and magnetism, they're all part of the same light. Speaking of light, Newton's laws and universal gravitation had stood unfalsified for centuries. Newton was a titan. Everyone looked up to him. If you were going to talk about a genius the way we talk about Einstein now, for hundreds of years, it was Newton. Then along came a scraggly-haired German Jew who fled Germany just as the Nazis rose to power. And just like Faraday was fascinated by electromagnetism, this man was fascinated by the nature of light. Now, the actual nature of light had confused scientists for a long, long time. His quest to find out about what light really was changed the way we would look at the world forever. And that man was Albert Einstein. He showed that Newton's second law, that force equals mass times acceleration, is only true as velocity approaches that speed. That's the speed of light. And it turns out that the speed of light is the universal speed limit. You cannot go faster. And you can only go that fast if you have zero mass. So if you're you or me or anything else we know of that exists, if there's stuff in it, it can't ever go the speed of light. So Einstein also showed that rather than gravitation being an external force, it's really caused by space and time being the same thing. It's called space-time. And Einstein showed that space-time is curved by mass that happens to be in it. So gravitation is really a dip in the fabric of space-time. So if we look at these two discoveries, one was discovering that two things that we thought were totally separate were really the exact same thing, depending on how we looked at it. And the second was that, well, despite the way we look at the world, we're not seeing the whole picture.
After nearly 10 years of racking his brain, he found the answer in a new kind of unification.
Einstein came to think of the three dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Notice we have the moon revolving.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity.
So for all of human history, we thought space was pretty much flat. This floor looks flat here, right? But of course, any bit of mass in it, no matter how small, curves it, even if just a little bit. Space isn't flat at all. Enough mass will curve it, essentially, into a bubble. And we'll get to that close to the end. Now, after we had discovered some of these things, we went on to discover the third and the fourth fundamental forces. They dealt with things that were very, very small, but very important. The third is the extremely small force that binds all the positively charged protons together in the nucleus of an atom. We would expect like charges to repel violently that close. Think of sticking positive ends of a magnet together. Now think of using hundreds of positive ends of a magnet. That'll give you a bit of an idea what the strong force is really like. It's a very short-range force, but it's very powerful. We also discovered a weak force that causes radioactive decay and allows the birth of stars. Respectively, those are the strong nuclear force and the weak nuclear force. And that was kind of a big deal. Now, my last class didn't get this joke. Do you? Badger, badger, badger? Or is this internet meme too old for y'all? Oh, good Lord. I've actually gotten to the point where my internet memes are stale. Oh, that's it. Do you get it? You do! Excellent. So badger, badger, badger. What's the next bit? What kind of a cloud is this? Cloud. That's okay. Who can tell me what kind of a cloud this is? And Google badger, badger, badger when you get home. But what kind of, any ideas? What does it remind you of? A big stem and then a cap on top. What kind of a cloud is it?
Mushroom cloud.
It's a mushroom cloud, folks. This is what the strong nuclear force gave us when you start breaking those bombs. Atomic bomb. This down here, that's the ground. These, those are clouds that have been blasted aside by our mushroom cloud. Mushroom clouds aren't unique to atomic bombs. Any large enough explosion will create one if the conditions are right. This may not be an A-bomb. This may be a volcanic eruption. But it's the same sort of power release. Now, all through human history, light has been a tremendously powerful metaphor and a very important part of human society. Most likely, we didn't start modern society until we developed fire and could live with families in caves. We still talk about illumination, about enlightenment, about the Illuminati. When an artist wanted to show someone is holy, they put a ring of light around their head. But we didn't really know what light was at the start of the 20th century. In fact, it was confusing and contradictory. When we performed some experiments, light seemed to travel in isolated physical pieces called particles, individual bits of matter, just like bullets. But when we performed other experiments, light seemed to travel in energetic, spread-out patterns in space-time called waves. Just like how radio waves spread out in a circle, or a sphere rather, from the transmitting antenna. Just like if you drop a rock in a pond, waves spread out. This didn't make any sense. Scientists weren't sure what the heck was going on. So some of them coined the term wavicles as a joke, because it doesn't make sense. How could something both be a particle and a wave? How can I have something that's both here and all across the classroom at the same time?
We see particle-like behavior every day. Drop a ball on the ground and it follows a single trajectory. Leave your giraffe parked on the street, and when you come back, it's still there, just one giraffe. And we see wave behavior too. Toot your horn, and waves spread out through the air, carrying sound to the ears of anyone around. Or drive a boat through water, and waves travel outwards along the surface. But when it comes to the physics of the very small, what we see is a wave-particle duality. Sometimes very small things, we're talking electrons and protons here, behave like particles, and sometimes they behave like waves, flip-floppers. For example, if you release an electron, it'll travel outward as a wave through the room, but when it hits the wall, it'll only hit in one place. You started with one electron, after all. So what if sound had a wave-particle duality? When you shouted, the sound waves would spread outwards in all directions, but only one person could hear what you said. Or when you drove your boat through the water, the waves would travel like normal, but only hit the shore in one place. Now that would make for some pretty boring surfing. In the last video, I introduced the idea that really small things act sometimes like waves and sometimes like particles. So how can we actually picture this wave-particle duality of, say, an electron? Well, imagine our electron is a speck of dust in a raindrop. We know pretty well where the speck is, at first. But when the drop hits the ground, it'll spread out like a wave, and the speck of dust will be somewhere in that wave. So the speck, our electron, is guided by the wave. But there's still only one speck, and if you actually look for it, you'll only find it in one place. The wave will also tell you how likely you are to find the speck at any one point. If the drop splits in two, you're more likely to find the speck wherever there's more water. And that's pretty much how the wave-particle duality of quantum mechanics works. Each particle is guided by a wave, called a wave function or pilot wave, that determines the chances it'll be in a certain place or state. Easy, right? The hard part is figuring out the movement of the waves.
This is important. It's all based on probability. We can say it's probably here, but it could be here, it could be there. Heck, it could be here. We're going to get to why that's important, but what you need to understand is that any small particle, protons, electrons, photons, behaves as both a wave and a particle. Let me get to something else interesting about that, because it gets weirder. In a famous experiment known as the experiment with two slits, it's also known as Young's experiment, we took photons and we shot them down a tube. At the end of the tube was a photographic plate. So every time light hit it, it would record that. In front of the plate, we put a screen. We cut two small slits into it. Hence the experiment with two slits. Now, depending on how we did it and how we were looking at it, we got different results. Sometimes we would see what we expected from particles, from bullets. They would move with trajectories as if they were shot from guns, and they would all pile up in certain places, same as if you went to a shooting gallery and you were shooting through a certain slit at a target at the end. But sometimes when we set it up, we would see that they interacted, they had interference as if they were waves. Imagine dropping not one rock into a pond, but two, and what happens when those two waves crash into each other. But someone came up with a very subtle and a very elegant variation. he sent down one single photon at a time. So we knew it had to be a particle because there was only one. But the interesting thing is, over and over again, he repeated the same experiment again and again and again. And over time, it created the same pattern as if each individual photon had interfered with itself. Doesn't make any sense, but here's a bit of what I'm talking about. Anytime we have waves, so we have a light source that sends out waves. If they have two slits, you have a wave front forming out of each slit. And they bounce off each other. In some places they get bigger, in some places they get smaller. They create this pattern over here. What do we notice over here? Just tell me about the facts. What do we see? Dark and light. Okay, so they're bands of dark and light. Which tends to be bigger here? Which do we have more of?
Light.
More light. Yeah. What do you think causes that then? We have these bands of dark and light. More what causes more light?
Interference?
Essentially, yeah. Where there are two waves add up, we get more light here, less here, more there, and so on. Yeah. Based on the interference, we're either going to get more or less. And this only happens with waves. So what? Well, a single photon going through either of those slits should create individual holes. We should get our shooting gallery pattern. But that's only what we see at first. As we repeat it, this is what happens. What do we see here? Does this look kind of like a shooting gallery?
No.
Not at all. If you were standing here and here and just shooting at the end?
A little bit.
Well, kind of individual bullets. What do we see happening here? Do we see a pattern yet?
No.
No. What do we notice between C and D? What's starting to happen?
The pattern starting to form.
What pattern? What do we see by E?
The light and dark pattern.
The light and dark pattern.
It's kind of wavy.
It's wavy, absolutely. We have our light and dark pattern. What did we just say caused that light and dark pattern?
Interference.
Interference. What did we say it has to have? We need something to have interference. What causes interference?
Waves.
Waves. Does this pattern here look similar to this?
Yes.
It's the same pattern. So somehow we had one photon that was definitely a particle, was also acting as a wave at the exact same time. We dealt with the idea of having particles sometimes and waves sometimes, but the idea that something could both be solid and spread out and energetic at the same time, it made no sense. Now what we see is an interference pattern. And an interference pattern is only ever created by two or more wave fronts. That means that a photon can somehow not only be in two places at the exact same time, it can actually crash into itself and change its own behavior. And in fact, this shows that a photon can behave as both a wave and a particle at the exact same time. And this suggests that at a certain level, the very categories we normally use to describe reality itself are simply fundamentally and necessarily inaccurate. The phrases to sum that up are: the map is not the territory, the menu is not the meal. The world exists first, and we come up with ideas and with words to describe it. They're not always accurate, and it's important to remember that even in defining something, solid, wave, we have a bit of interpretation, of guesswork to do. We're not always certain. And if we're lucky, we're all learning and all in the middle of the learning curve forever, if you keep trying, and it requires work. But we see that there's this interesting union on a few levels. We see that space and time are the same thing. We see that electricity and magnetism are the same thing. And we've seen that certain things can be in two places at the same time and can interfere with themselves at the same time. Now, yeah, we do now know that a single thing can be in two places at the same time and can be solid and self-contained at the same time as it's spread out. Even stranger, equations discovered by Richard Feynman, called the sum over many paths model, shows that that photon doesn't take a path from my laser pointer to your eyes. What really happens is that the photon travels in an infinite number of paths in space-time that, when added up, give us the appearance of the path it travels. And that means it goes literally everywhere and every when in universe at the same time.
Questions of light and motion 10 years in the asking suddenly began to come clear. By 1905, Einstein simply accepted that the speed of light was absolutely constant, everywhere in nature. But that left the problem of motion. There is no difficulty measuring speed here on Earth. As far as a juggler at the castle can tell, he is standing still while his twin on the boat juggles away at 5 miles an hour. Meanwhile, the juggler afloat sees it differently. He stands still while the lake, the shore, and his twin recede at 5 miles an hour. That's the principle of relativity. The idea that both jugglers can use the same laws of physics to describe the motion of the pins. But light is the wild card. Einstein was convinced that if a beam of light passes both the juggler at rest and the juggler in motion, each would measure the same speed for light. But how could that work? What happens to allow both jugglers to agree on the speed of light? That's when the breakthrough came. Speed is simply a measure of distance traveled in a unit of time. And Einstein realized that if the speed of light never changes, then something else must vary. What if, Einstein asked himself, the speed of light is constant, but the flow of time is not?
Now, the idea that you were just given, not necessarily about time changing, but about light always being the same speed, is probably a little bit odder than it seems to you at first glance. Now, it turns out that light is very, very special. We know that in a vacuum, light will be measured as having a speed, c, that's the c equals mc squared, that's roughly 300 million meters per second, or about 600 million miles an hour. Now, we know that for comparison, 600 million miles is the distance of about roughly 120,000 round-trip drives between New York and LA. Now, if you were to make those drives without sleeping, stopping for gasoline, food, to use the bathroom, doing anything but driving, it would take you 540 years. Light does that in a single hour. That's not why light's so cool, though. The real reason light is so interesting is that nothing else really acts the same that we know about. If a truck is going 70 miles an hour on Mopac and you're going 60, you measure it as going 10 miles an hour faster than you. If you accelerate it to to 70, you'll see you're going at the same speed as it. Seems simple. What's my velocity right now? 0, right? How do you know?
You're saying it's still
Relative to what?
our position.
Relative to your position. Right. Relative to your position, I'm not moving. Is the Earth moving now? Yeah, the Earth is moving at hundreds upon hundreds of meters per second. So we are moving. Do you think our galaxy that has our solar system in it is also moving? Yeah, it's moving really fast. So we can sit here, and if we're moving at the same speed, we don't detect any motion. It's called being in the same inertial system. Light doesn't work that way. No matter what what you're doing, light is different. It doesn't work the same way as trucks, cars, you and me, or anything else we know. If you were to accelerate to 1 meter per second less than the speed of light, light will still be going the speed of light faster than you. If there's a truck going 100 miles an hour on the highway and I accelerate to 99, how much faster than me is it? I'm going 99 and it's going 100, how much faster? 1. We would expect it to be 1 meter per second faster at that point. But no. No matter how fast you go, light always goes the speed of light faster than you. And what's more, if two people are moving at different speeds and in different directions, they'll still measure light as having the exact same speed. Now, this means that the view of the world from a photon's point of view is really strange. If time stands still, if a photon can be in more than one place at once, if it travels everywhere and every when in an infinite number of paths, if nothing ever moves compared to a photon,
Here, finally, was the answer to Einstein's first question about light. What would happen if he could ride a beam of light? Nothing, for he never could. At the speed of light itself, length shrinks to 0, and time stands still.
at the speed of light, there's no such thing as time, and all length is 0. That is, the entire universe has no distance if you're traveling it. No time, and it takes no space to be anywhere you want, instantly. This makes absolutely no sense for the world we've evolved in. We're an evolutionary relative best fit. We are clever apes. We evolved as hunter-gatherers. We have the senses that we need for that role, relatively compared to our competition. We don't perceive these sorts of things. And it's only now in humanity's history that we're starting to get a picture of how the world differs from the way we see it. And it is strange. It's strange as a singing giraffe. And the giraffe is on fire, and also there are ninjas. Once you start getting into it, you'll see that to a photon, nothing is moving, ever. But we also know that as we approach the speed of light, time slows down and then stops. So in a very real sense, a photon, which can be in more than one place at the same time, which can travel through an infinite number of paths to get from point A to point B, that photon somehow sees all of reality from the beginning of time to the end, spread out and unchanging. That raises a very interesting question. If then a photon sees everything and nothing ever changes, how do things change? How do we grow old and die? How are people born? How is there change if from a photon's point of view, nothing ever moves? And this, of course, is our fire-breathing giraffe. Now, the point about how what might be true for a photon's point of view might not be true for us is important. Just like we can have a particle and a wave, just like we can have space and time, just like we can have electricity and magnetism. Unification answers many of our questions and often leads to some more. And that's not all. If we look at the smallest distances, smaller than you can even conceive of and you can think of, the tiniest, absolute smallest possible level of space. Space isn't flat like we think the floor is, or curved like Einstein told us. Space looks like this. Space is boiling, it's bubbling, it's seething. We call it the quantum foam. At that level, space is essentially random. You can have peaks and valleys, hot and cold. It's chaos. There's no way to predict it or to describe it thoroughly without stopping it somehow, which we can't do.
And as we'll see, quantum mechanics paints a picture of space so drastically different from general relativity that you'd think they were describing two completely separate universes. conflict between general relativity and quantum mechanics, we need to shrink way, way, way down in size. And as we leave the world of large objects behind and approach the microscopic realm, the familiar picture of space in which everything behaves predictably begins to be replaced by a world with a structure that is far less certain. And if we keep shrinking, getting billions and billions of times smaller than even the tiniest bits of matter, atoms and the tiny particles inside of them, the laws of the very small, quantum mechanics, say that the fabric of space becomes bumpy and chaotic. Eventually, we reach a world so turbulent that it defies common sense. Down here, space and time are so twisted and distorted that the conventional ideas of left and right, up and down, even before and after, break down. There's no way to tell for certain that I'm here, or both places at once. Or maybe I arrived here before I arrived here.
At this level of reality, all our rules are off. Nothing makes sense to us anymore, and predictability becomes impossible. This is the strangest level of reality for that reason. Outside of a black hole, this is some of the most interesting stuff we can get to. We're going to talk about black holes in a bit. One of the really interesting things about the quantum foam, though, foamy, is that it turns out from out of the foam, we get something called virtual particles. Virtual means not real, same as virtual reality. These are created out of quantum vacuum fluctuations. Literally out of nothing, we get virtual particles. And they're always created in pairs. They're opposites called antiparticles. Think matter and antimatter. And they touch, and when they touch, they obliterate each other. They annihilate. They're gone. But what's left and what's created are two photons. So out of nothingness, we get something. Inevitably. And that something is light. Now again, we're not evolved to perceive this directly. But that means that there's no such thing as nothing. And even the emptiest spaces of the world are radiant. It would be cool if we could see that. Well, that's just photons, right? Turns out, no. Heisenberg, and that's physics, not math, discovered what we now call the uncertainty principle. The uncertainty principle says that for any subatomic particle, we can either know its position or its momentum, but not both. In fact, the more we know about how something is moving, the less we can know about where it is. And that doesn't have to do with our equipment, or with our eyesight, or with anything else. Uncertainty is fundamental to reality. We can't avoid it. And that means that perfect knowledge of anything is impossible. Instead, we talk about probabilities. So especially in your own lives, if you find yourselves confused about things, it's normal. Knowing for sure is not something we can do past a certain level.
Quantum mechanics is weird, right? But did you know that some of its supposed peculiarities are not unique to quantum physics, but are just properties of waves in general? Take the uncertainty principle. It says that the better we know where a particle is, the less we know about how fast it's going. There's a limit to how much we can know. But this isn't just quantum weirdness. It happens all the time with normal everyday waves. Remember that the frequency of a wave is how close the wave crests are to each other. A low-frequency wave doesn't have nearly as much oomph as a high-frequency one. And the position of a wave is, well, where the wave is, mostly. So where exactly is a wave? It's spread out everywhere, right? Okay, but for a wave pulse, it's pretty easy to see where the wave is. So now that we know where the pulse is, what's its frequency? Well, a localized pulse doesn't really wave, so we can't measure the frequency of its crests. And that's the uncertainty principle in a nutshell. You can either know where a wave is, or where it's going, but not both at the same time.
That's our basics. You can know what something is, or how it's changing, but knowing both at the same time, especially when we get to the quantum level, becomes impossible. can know where it's going or where it is, but not both. It gets weirder. Uncertainty is due to something called a wave function. That's because all subatomic particles, called quanta, hence quantum dynamics, or quantum mechanics, behave both like waves and particles, just like photons. Now, a wave function exists in a state of uncertainty before we measure it and check it. And that wave can be thought of as the result of vector addition for every particle in the system. Because it's what's happening with everything in the system, we call it the state vector.
Then, in the late 1920s, all that changed. During those years, physicists developed a new theory called quantum mechanics, and it was able to describe the microscopic realm with great success. But here's the thing. Quantum mechanics was so radical a theory that it completely shattered all previous ways of looking at the universe. Einstein's theories demand that the universe is orderly and predictable. But Niels Bohr disagreed. He and his colleagues proclaimed that at the scale of atoms and particles, the world is a game of chance. At the atomic or quantum level, uncertainty rules. The best you can do, according to quantum mechanics, is predict the chance or probability of one outcome or another. And this strange idea opened the door to an unsettling new picture of reality.
Now remember, all through human history, we've been fairly certain that the world around us is what it is, and that things are fairly predictable. That's part of why Newton was so important. He gave us the math that will tell us what happens reliably given our variables. But it turns out it's weirder than you might think. See, what's interesting about the state vector, the vector that shows us how everything in a system is changing, is that observation or measurement collapses it into one specific situation that we call an eigenstate. But before we collapse it, what's really weird is that before it's collapsed into just one reality, every possible reality exists at the same time, stacked on top of each other. We call that superposition of states. It appears to be real. Real as radio, even though we can't see that either. But if it is true, then multiple realities exist all around us, all the time, until we choose to do one thing or another, or until we measure or observe, therefore deciding which it is. And we'll get to that. But if there are these multiple realities, where do they go?
It was so unsettling that if the bizarre features of quantum mechanics were noticeable in our everyday world, like they are here in the Quantum Cafe, you might think you'd lost your mind.
The laws in the quantum world are very different from the laws that we are used to. Our daily experiences are totally different from anything that you would see in the quantum world. The quantum world is crazy. It's probably the best way to put it. It's a crazy world.
For nearly 80 years, quantum mechanics has successfully claimed that the strange and bizarre are typical of how our universe actually behaves on extremely small scales. At the scale of everyday life, we don't directly experience the weirdness of quantum mechanics. But here, in the Quantum Cafe, big, everyday things sometimes behave as if they were microscopically tiny. And no matter how many times I come here, I never seem to get used to it. I'll have an orange juice, please.
I'll try.
I'll try, she says. You see, they're not used to people placing definite orders here in the Quantum Cafe because here, everything is ruled by chance. While I'd like an orange juice, there's only a particular probability that I'll actually get one. And there's no reason to be disappointed with one particular outcome or another, because quantum mechanics suggests that each of the possibilities, like getting a yellow juice or a red juice, may actually happen. They just happen to happen in universes that are parallel to ours, universes that seem as real to their inhabitants as our universe seems to us.
Gets weirder. Here, kitty, kitty, kitty. A man named Erwin Schrödinger came up with a famous thought experiment. A thought experiment is something you don't actually do, you just work the math on. It's now known as Schrödinger's cat. Now, Schrödinger's cat is put in a box with an atom that has a 50-50 chance of decaying and giving off radiation. If radiation is detected by a Geiger counter, a bottle of poison gas will be opened, and the cat will die. But until we open the box, until we measure, until we observe, the cat is both alive and dead at the same time. Not half alive and half dead, 100% alive and 100% dead. It's only after we open the box and remove that uncertainty that we select which eigenstate we live in, and of course whether or not Fluffy made it through with us. Now what that looks like from Fluffy's point of view is another question.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrödinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode, or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode, and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer, please?
Nope, no answer. We don't know. We don't know. There are several different interpretations. There are many different ways to look at it, and we're not sure. We do know, as an absolute certainty, that before we collapse the wave, we have multiple realities, multiple eigenstates, existing on top of each other, a superposition of states. We know that there's something that seems to be inherent in consciousness or measurement or observation that chooses one or the other. We don't know where they go. We don't know if they go anywhere or just disappear. We don't know what causes our observations to collapse, and it gets more interesting. Before we open the box and observe it, the cat's fully dead and fully alive. And the photons solid and spread out, and in an infinite number of places at the same time. But our universe also isn't the only one. It's correct. The math behind inflation, which shows how the Big Bang happened, shows us that the Big Bang was not an isolated event. In fact, if the math is correct, then it seems to be there have been an infinite number of Big Bangs, and they're still happening. And that would mean that our universe is only one of many, many, many other possible universes. That we live in a multiverse, not a universe. And that maybe in one universe you are Batman.
I am Batman.
But of course Batman wishes he was...
It's almost as if we were living inside a loaf of bread.
might be like a slice of bread, just one slice, in a much larger loaf that physicists sometimes call the bulk. And if these ideas are right, the bulk may have other slices, other universes, that are right next to ours. In effect, parallel universes.
Not only would our universe be nothing special, but we could have a lot of neighbors.
Holy crap.
Pretty much. It gets weirder. Three scientists, Everett, Wheeler, and Graham, came up with what's now known as the many worlds hypothesis. And it may actually be true that you, and you, and every one of us is you out of one of an infinite number of copies. And that every time the state vector collapses, a new universe is created for it. So that everything that can happen does. And that would mean that you would be you. But what would that mean? If every time you chose between pancakes and cereal for breakfast, you were in a different universe, what would it mean to be you or your twin? What would make you who you are? Of course, others argue that the superposition of states is real enough, but that the alternatives simply vanish as if they never existed once we determine one. Yes?
So, like, what about clones and stuff like that? How does that affect that?
That would be different. Here we're talking about not so much a physical you, more as the idea of you between infinite universes. What would you be like if you were born, in Russia versus here? That sort of thing. Clones, more it's biological or essentially duplicating DNA. Yes?
What about twins? Like twins from different universes?
Well, we don't know. We don't know for a fact that this is true. This is one of the interpretations. If it is, it leads to questions like that. I would say that if that's true, then probably it would be the choices we make that determine who we are and where we find ourselves. So I could be persuaded otherwise. Don't let me tab back in. Now, we're not done.
And even in our own universe, quantum mechanics says there's a chance that things we ordinarily think of as impossible can actually happen. For example, there's a chance that particles can pass right through walls or barriers that seem impenetrable to you or me.
There's even a chance that I could pass through something solid, like a wall. Now, quantum calculations do show that the probability for this to happen in the everyday world is so small that I need to continue walking into the wall for nearly an eternity before having a reasonable chance of succeeding. But here, these kind of things happen all the time.
You have to learn to abandon those assumptions that you have about the world in order to understand quantum mechanics. In my gut, in my belly, do I feel like I have a deep intuitive understanding of quantum mechanics? No.
And neither did Einstein. He never lost faith that the universe behaves in a certain and predictable way.
Einstein's famous quote on quantum mechanics was, he didn't believe it because God does not play dice. Einstein pretty much went to the end of his life without accepting that quantum mechanics was correct. It is. Now we know that it is because we have experimental proof, because it's what underlies a lot of our modern technology. We're not done yet. We've got some more weirdness for y'all. Recently there was a debate between two scientists, Leonard Susskind and Stephen Hawking. Probably heard of Stephen Hawking. Now Hawking argued that information for particles that fall into a black hole is lost forever. Just gone. Destroyed. Susskind argues that there's conservation of information. And that it was the same as energy or momentum. Turns out Susskind was right. He proved that conservation of information is as solid as conservation of energy. It might just be as important. Turns out that as matter falls into a black hole, space-time bends so much that time stops at the edge, which we call the event horizon. So to an outside observer, matter never quite falls into the black hole. But at the same time, any matter at the event horizon really is sucked into the black hole. So the cat is both alive and dead, and the photon is a particle and a wave at the same time. But in a very real sense, matter is both torn to pieces by the black hole, and it exists on the skin of the black hole as pure information, as long as the black hole exists. Now, black holes do evaporate through a process called Hawking radiation. But it doesn't stop there. Information in a holograph, which is how it's stored at the edge of a black hole, is interesting. Because if you take any one point, essentially it has the information for all the points. A holograph is an interference pattern, just like the waves we were looking at. And the pattern is the same at all points, because it has to be the whole pattern. If you imprinted a holograph on a pane of glass and shattered it, your smallest piece of glass would still have the whole picture on it. And that means that thinking of separate things in a holograph is inaccurate. There's only the relationship, how they all fit together. If we were to take a holograph of this class and then remove one person, the whole holograph would then be different. Holograph is everything and how it interrelates. And so in terms of information stored at the edge of a black hole, difference, identity, and individuality all dissolve. Information becomes interrelated and interpenetrating. Everything's got something to do with each other, everything's connected, nothing can be separated. It gets weirder. Because in the tiniest fraction of time before the Big Bang, our entire universe was a massive amount of matter crammed into a very, very small radius. That radius is known as the Schwarzschild radius. Any amount of matter compressed into that radius, and it's different depending on the amount of matter, more matter, bigger radius, bends space-time and forms a singularity. Singularity, in fact, bends space-time infinitely, to the point where not even light can escape.
Unified theory.
You probably know that.
And nowhere is this more evident than in the depths of a black hole. A German astronomer named Karl Schwarzschild first proposed what we now call black holes in 1916. While stationed on the front lines in World War I, he solved the equations of Einstein's general relativity in a new and puzzling way. Between calculations of artillery trajectories, Schwarzschild figured out that an enormous amount of mass, like that of a very dense star, concentrated in a small area, would warp the fabric of space-time so severely that nothing, not even light, could escape its gravitational pull.
And of course, the black hole. Black hole is essentially a singularity with an event horizon, a veil. Something that we can't see past. But the Big Bang was a naked singularity. It had no event horizon. And there's strong evidence that all the information in our universe is stored as a holograph on the skin of the universe. But remember, space and time are one thing, space-time. And our universe represents all the space-time we have. So in a very real sense, it's nonsense to talk about something that happens before or after universe. There is no before or after. So from a very real point of view, it seems that the holograph of the information that's you and me and everything we ever know or might know is beyond time and space as we think of them. It's beyond change. And so, if we are living inside a singularity, if singularities store information holographically, if the cat is both alive and dead at the same time, if a photon can be here, there, and everywhere at the same time, what does that mean we are? What is it to be alive and aware in a world like we find ourselves in? And I would suggest that perhaps, just as the cat is alive and dead at the same time, just like the photon is a wave and a particle at the same time, perhaps that we are likewise limited, mortal, and bound to one single lifetime. And at the same time, we are boundless, eternal, and one essential and inseparable portion of the cosmos. That perhaps it's our categories themselves that don't make sense anymore. And that we need to start accepting that the world around us is bigger and stranger than we've ever imagined before. Perhaps.